Yeah. So today we will see a combination circuit called as a decoder. Okay, so we'll study about this decoder. So we'll see how to design this decoder. So what is the meaning of this decoder, and we'll check out the problems related to this decoder, right? So the topic of today's decoders. Right. So what is a decoder? Okay. So generally decoder is nothing but it is a combination circuit which will convert, which will take n bit input here, and those n bits will be converted into 2 power n coded outputs. Okay. So we'll be having n inputs. Okay. So n inputs, and those n inputs will be taken here and converted to 2 power n outputs. 2 power n outputs. Okay, so 2 power n outputs is the maximum one. So less than 2 power n outputs is also possible. Okay, so generally, so 2 power n outputs is the maximum outputs that will be generated by the decoder, but less than 2 power n is also possible. Okay, so that is a decoder here. A decoder is a combination circuit. Combination circuit which accepts n inputs and converts into 2 power n coded outputs. Okay, so there is a basic general definition. So n inputs and 2 power n outputs are less than or equal to. I mean, so it may be less than 2 power n or equal to 2 power n. So it may generate those inputs here. Okay, for example, if there are 2 inputs, it will generate 4 outputs. Okay, it will generate 4 outputs in case of the decoder here. Okay, so getting my point?
Yes, sir.
Yeah, sir.
Yeah. So screen is visible, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. We'll check an example here. So we'll check an example of 2 to 4 decoder. Okay. So we'll check example of 2 to 4 decoder. Okay. So generally what we'll write here is 2:4. 2:4 decoder. Okay. So this is like 2 is n here. Okay. So 2 into 2 power 2. I can't use symbol of power here. Okay. So into 2 power n here. Okay. So 2 into 2 power, I mean n into 2 power n is nothing but 2 into here n is equal to 2 here. Okay. So it is 2 to 4 decoder. So first of all, what I had to do, I had to draw a truth table here. Okay. I had to draw a truth table for this one. Okay, so truth table will be like this. So 2 inputs and 4 outputs. Okay, so the inputs will be xy. Okay, and the outputs will be, I'll put it as d naught, d1, d2, and d3. So these are the inputs and these are the outputs here. Okay, so the inputs are the combination 0. So when you have two inputs, these are the combinations 0 0 0 1. So 1 0 1 1. Okay, so for a decoder, so what we said is with two inputs it will generate four outputs here. So only one out will be active at a time here. Okay, so it will generate four outputs, it's fine, but it will generate only one output at a time here. I mean one output will be active at a time, so remaining all outputs are inactive. Okay, so active in the sense, so here active in the sense it is 1 and remaining all are zeros here. Okay, so in this case, so d naught is equal to 1 and remaining all three outputs are equal to zeros. Okay, in a similar way, so here 0 1, for 0 1, this is d1 is equal to 1 and remaining all are zeros. And for 1 0, the combination of inputs 1 0. Okay, so this is 1, d2 is 1 and remaining all are zeros. Okay, and for xy is equal to 1 1, this is 1. Okay, so decoder is capable of is a combination circuit that converts binary information from the n inputs to a maximum of 2 power n outputs. So 2 power n unique or distinct outputs. Okay, so we can't say that so no two conditions will be true at a time. Okay, if d naught is 1, so remaining all should be equal to zeros here. Remaining all are zeros. Okay, so for two inputs, these are for the two inputs. So if I take the k maps for this, so k maps or if I derive the equations for this, for d naught the equation will be equal to, so what is the equation for d naught? So if this is the truth table, so for 2 to 4 decoder, now tell me the equations for d naught, d1, d2 and d3. So మీరు truth table లో ఏం చెక్ చేయాలి అంటే, so what we had to check here is, so we had to check once in the truth table here. So d naught is 1 only for the combination of inputs xy is equal to 0 0, right? Yes or no? So record అవుతుందా? Yeah, for the combination of inputs 0 0. Okay, so d naught is equal to, so what is d naught now?
X bar, Y bar.
X bar y bar. Okay, so d naught is 1 for the combination of inputs xy here. So xy is like 0 0, so x 0 aithe, so it is x bar, y 0 aithe, it is y bar. So we had to perform the multiplication of this input combination. So these are min terms here. Okay, and d1 is
X bar, Y.
X bar Y.
so d1 is equal to x bar y. So d2 is equal to
X, Y bar.
X Y bar.
yeah, x y bar, and d3 is equal to
X Y.
Y.
xy. Okay, so this is the equation, so we have to draw the diagram now. Okay, so diagram, so we'll follow this method here. So wait, diagram of 2 to 4 decoder. So generally we'll draw the diagram first, so then we'll go for the block diagram. So we'll see how the block diagrams will be. Okay, so this is diagrams will be like this. This is x, this is y, Okay, so you draw this diagram like this. So 2 to 4 decoder, and this is X bar. To give it to an inverter, and this is Y bar. Give it to an inverter here. Okay, so D naught. So 1 minute. Thank you, Azan. Let's కూపన్స్ 11:15 క్లాస్ అయిపోతుంది ఉంటావా yeah sorry fine so this is the circuit here. So X, we'll take the circuit like this. So D naught is X bar, Y bar. Okay. So we need a multiplication of these two. So we need AND gates here. So we need 4 AND gates. This is 1 AND gate, second AND gate, so third AND gate, and fourth AND gate. So this should be D naught, D1, D2, and D3. Okay. So D naught is X bar, Y bar. So this is X bar. Give a connection to this, and this is Y bar, and give a connection to this. So this is D naught. So what is D naught? So D naught is equal to X bar, Y bar. Okay. So D1 is X bar Y. So this is X bar, and this is Y. Okay. And D2 is X Y bar. This is X here, and this is Y bar. And D3 is XY. This is X, and this is Y. Okay, so this is D naught, D1, D2, and D3. Clear?
Yes, sir.
Okay, so take this diagram also. Like this is a 2 to 4 decoder. So now we'll do a 3 to 8 decoder. So mirror in 3 to 8 decoder. So we'll be having 3 inputs. We'll be having 8 outputs. So D naught to D7. So one will be activated time. Okay, so derive the equations from D naught to D7. So same thing, and draw the diagram. So I'll be giving 2 minutes of time. So do that. So 2 to 4. So 3 to 8 decoder. So X, Y, Z. D4. D3, D4, D5, D6, D7. So the input combinations. So here, I mean, lateral entry people, you don't worry. Like we already koncham idea ఉంటుంది, but if you are really backward, like so, we'll definitely have the classes. So when you come here. So meanwhile, listen to those recordings. So we can అర్థమైతే అంత అర్థం చేసుకోండి. So these are the things you have to do first. So first of all, input combinations, 3 input ichara, 4 input ichara. So first of all, you have to do all those things. So only one input will be active. So first of all, D1 is active and remaining all are zeros. Next, D1 is active. Next, D2 is active. Only one output will be active at a time for a given input combination. So we'll be having 8 input combinations here. So 8 input combinations ki oko input combination ki oko output active ఉంటుంది. Okay, so fill the remaining things. The remaining truth table. Okay, so what is the value of D naught?
X bar, Y bar, Z bar.
So D naught is equal to, so X bar, Y bar, X bar, Y bar, Z bar. Okay, so D1 is equal to,
X bar, Z, Y bar, Z.
yeah, X bar, Y bar, Z. So you can see here, this is X bar, this is Y bar, and this is Z. We have the remaining equations and draw the diagram. So D2 is equal to X bar Y Z bar, X bar Y Z bar. The small letters and capital letters. Okay. In the similar way, D7. So remaining terms, you write remaining terms. So D7 is equal to XYZ. Clear?
Yeah, sir.
Yes, sir.
Yeah. So or will you do that? So I'll show like this. So take this. So X, Y, Z, and I take this is X, Y, Z. So this is X bar. This is Y bar. This is Z bar. Okay. So if I take the example of D naught here, so we'll be using 8 AND gates here. So 8 AND gates are used here. So all of them are bars here. So there's X bar, Y bar, Z bar. This is X bar, Y bar, Z bar. So the D naught. In a similar way, if it is D7, this is X, Y, Z. So this is X, this is Y, and this is Z. So select X, Y, Z. So this is D7. Okay. In a similar way, if it is D6, so this is X, Y, Z. So this is X, this is Y, and this is Z bar. Okay. So draw the diagrams, gates. Okay. So neat drawing. Okay. So this is a normal 3 to 8 decoder. Okay. So this is a normal 3 to 8 decoder, and what we can do here is we can construct a 3 to 8 decoder using NAND gates also. So this is construction using AND gates. So we have to construct the gates also. We can construct the decoder using NAND gates, and we'll have a input called as enable input. Okay, so with the help of that, we'll design that. Here,
Yes, sir.
Yes, sir.
yeah, decoder. So next, design of decoder using NAND gates and enable input. So construction of decoders using NAND gate. Okay, so we'll see the construction of decoders using NAND gate. So NAND gate is a inversion of AND. So generally, if I put an inverter, so after NAND gate, so AND gate, so we'll get a NAND gate. Okay, so it is inversion of AND operation. So inversion of AND will give you the NAND gate. So we'll see a 2 to 4 decoder with NAND gates, and we'll use a extra input called as enable input. Okay, extra input called as the enable input. So when we use an AND gates, the truth table will be reversed. Okay, the truth table will be reversed. So so in the truth table range comes, so what we have seen in the earlier truth table. So whenever I have 0 0, so D0 is 1, and remaining D1, D2, and D3 all are zeros. Okay, and if it is like 0 1, so D1 is 1, and remaining all are zeros. So here in case of NAND gates, it is reverse case here. Okay, so when it is enable, will represent with a 0. When it is disabled, it will represent with a 1. In case of NAND gates. Okay, for NAND gates, 0 is enabling and 1 is disabling here. Okay, so we'll see the 2 to 4 decoder. Okay, so I'll put it as A and B. So I'll mention additional input called as enable. So I'll let you know what is meaning of enable input here. So D0, D1, D2, and D3. Okay, so enable in the sense, so if it is active, so all the I mean all the things will be normal. If it is inactive, so what happens here is, so all the things, whether inputs A and B, so whatever the inputs we have for A and B, all of the outputs are inactive. Okay, so just like what I can say, you can say main of your okay, main switch ఉంటుంది ఇంట్లో. Okay, so what happens if I use a main switch here? If the main switch is off, so if I switch on the lights, fans, or whatever the lights and fans, or whatever the things here, so there is no use, right? So we'll not get any kind of output, so power output. Okay, so if it is a main is on, so depending upon which switches are on and off, which switches are on and off, then only we will get the respective outputs there. Getting my point? Okay, so this is like main power supply. So in your home, so enable signal is like main power supply. So when it is on only, so irrespective of the things only, it will happen. So when it is off, like when it is disabled, okay, so when it is disabled, so all the inputs, I mean all the outputs will be disabled irrespective of the inputs, irrespective of the inputs here. Okay, so here in case of when I'm dealing with the NAND gates here, so 0 is enable and 1 is disable. So or I can say it 0 is active and 1 is inactive. Getting my point?
Yeah, sir.
Yeah,
Okay, so here in case of this one, so what I have to do here is, so enable means, so enable 1, so I'll say that 1 is inactive here. So when enable is inactive, irrespective of the values of A and B, I'll take it as don't catch. So don't catch means ones and zeros. If I have A as don't catch, so whatever the inputs I have for A and B, all the outputs will be inactive here. Inactive in a sense, so they'll be equal to 1. They are equal to 1. Okay, so when enable is equal to 0 only, so then these inputs will work here. Okay, so inputs like 0 0, when it is 0 0, so D naught is 0. So I said that we are using NAND gate, so hence D naught is equal to, D naught is active here, so active is represented by 0 here, and remaining all are equal to 1. Okay, and here enable 0. So when AB is equal to 0 1, so D1 is active here and remaining all are inactive. And enable 0 1 0, and okay, so enable 0 1 1, so 1 1 1 0. Clear?
Yes, sir.
sir.
So this is a truth table here. Okay, now I have to draw this one diagram for this. Okay, so what I have to take here is here, what is the value of D naught? So what is the value of D naught we'll get here? The same thing. Okay, so here instead of checking for ones here, we'll check for zeros. We'll check for a 0 here. Okay, so we'll check for zeros in case of D naught, D1, and D2 and D3. Okay, so they are the same things, like they'll not change. Like D naught is equal to, so A bar, B bar, B naught is equal to A bar, B bar, and D1 is equal to same thing, like A bar, B,
A bar B.
and D2 is equal to A
AB
B
bar.
bar, and D3 is equal to AB.
AB.
Okay, and we have one input called as enable input. Okay, we have one input called as enable input. We have to include that in the diagram. Okay, so diagram will be like this. So we'll be having enable. Okay, which enable should be irrigavati, like so it should be 0. So I'll use an inverter. I have enable and I have A. So B. So I'll be using NAND gate here. So this is A bar. So B and B bar. Okay. So if I need D naught here, so use an AND gate. So this is D naught. Okay. So enable should be equal to 0. So for all here, so the first thing, so enable should be equal to 0. Okay, and it is A bar and B bar. So A bar, so B bar. Okay, and D1, so enable is 0, NAND gate, and A bar B. This is A bar and this is B. Okay, so remaining cases, this is D2, A B bar, so enable should be there, A B bar, so this is A and this is B bar. Okay, and the last one, it is D3, D2, D1. Okay, so this is AB, this is B, this is A, and this is enable. It's enable bar. Okay, so this is a 2 to 4 decoder using enable input and NAND gates. Clear?
Yes, sir.
So any doubts in this? So please let me know any doubts in this. So when I'm using AND gates and NAND gates, so the operations will be opposite. Okay, the operations will be opposite. Clear?
Yes, sir.
Yes, sir.
Okay, so now we will see how to implement these Boolean functions or any kind of circuits using this decoders. We'll see one or two problems now. Two minutes. Yeah. So we'll see two sets of problems here. So the first set is like design take down this problem. So design a full adder circuit using decoder and logic gates. Using decoder and logic gates. Right? So there is a problem. So where do you last class we have seen this two table of full adder. Okay. So there is another name for decoder here. So decoder, so take down this name. This is important. So decoder is called as min-term generator. Okay. So why it is called as min-term generator? So what is the meaning of min-term? So what is the meaning of min-term? Yeah, tell me the meaning of min-term. So what is min-term and what is max-term? So I told you the definition. Even there.
And operation between possible input combinations.
Yeah, it is the AND operation between the inputs here. So what are the possible input combinations? Will perform AND operation. The AND operation in the sense it is a multiplication of the inputs here. Okay, so that is called as a min term here. Okay, so decoder is called as a min term here. So if I say that check the earlier example. So what is D naught? What is D naught? What is D1 and what is D3? So 2 to 4 decoder. So what is D naught and what is D1? What is D2 and what is D? So D naught for a 2 to 4 decoder. So D naught is equal to X bar Y bar. So X bar Y bar ante 0 0. Okay. So it is equal to M naught. So what I can say? What I can say here is M naught. Okay. So min term is nothing but it is a like M naught is nothing but 0 0 0. Okay. So which I can write it as a X bar Y bar Z bar or X bar Y bar. And a D1 is equal to what I have written there. So it is 0 0 1. So 0 0 1 ante it is nothing but X bar Y bar Z. Okay. Or I can write it as a 0 1. Okay. So it is X bar Y. I mean 2 to 4 decoder or 3 to 4 3 to 8 decoder. So we'll be having the min terms there. Okay. So generally, so you can see here, right? So 2 to 4 decoder. Take this 2 to 4 decoder. So if I say that D naught, D1, D2, and D3. Okay, so what are the outputs I'm getting? I'm getting the outputs as D0, D1, D2, and D3. Okay, so what are the outputs I'm getting? It is I'm getting it as 0, 0, 0, 1, so 1, 0, and 1, 1. So I'm getting all the outputs here. So I'm getting 0, 0 output, 0, 1, 1, 0, and 1, 1. That is nothing but all the min terms are, we are getting the outputs as all the min terms here. Okay, so all the min terms are generated as outputs here. So yes or no?
Yeah, sir.
Yeah. So D naught is generating M naught. So what is the meaning of M naught? Small M naught. So what is the meaning of M naught? So it should be equal to 0 0. So 0 0 ante it is x bar y bar.
Y bar.
Y bar.
Okay. Next D1, it is generating M1. So what is meaning of M1? It is 0 0 1, or we can say it as 0 1. So 0 1 ante, so it is x bar y.
X bar Y.
X bar.
So in a similar way, D2 is generating x2, and I'm sorry, M2, and D3 is generating M3.
M3.
So all the minterms are generated using this decoder. Hence, it is called as the minterm generator. Okay, and it is called as the minterm generator. So, getting my point?
Yes, sir.
Yes, sir.
So now what we have to do? So we have to design a full adder using decoder and logic gate. So first of all, I need the truth table for the full adders. So inputs and outputs column. So what are the inputs for 3 inputs for we'll be having for a full adder, and we'll be having 2 outputs. So sum and carry. So we did this right yesterday. Okay. So we'll write the input combinations here. 0. These are all the minterms. 1 0 1. Right. So now what we have to do? So we have to check this sum and carry. So you know this sum and carry outputs, right? So 0 0 0 ite. So sum is 0, carry is 0. Okay. So 0 1 0 0 1, sum is 1, carry is 0. Okay. So 0 1 0. So it is also sum is 1, carry 0. 0 1 1. It is sum is 0, carry is 1. Okay, so 1 0 0, sum is 1, carry is 0. So 1 0 1, sum 0, carry 1. So 1 1 0, there's sum 0, carry 1. Okay, and 1 1 1, it is sum 1, carry 1. This is truth table. We got this truth table, right? So truth table they'll say the manako.
Yes, sir.
Right?
Yes,
So
sir.
we have inputs and outputs. This is the truth table of the full adder here. Okay. So what I can write with this full adder here is, so I can write the full adder like this. So I'll not write the equations. So what I can write here is, so sum is equal to, so sigma. So sigma symbol in the middle. So what I can say here is, so sigma of, so what are the minterms for sum here? So sum KV minterms unna ikkada manaku. You can check here. We check here. What are the sum outputs? Ekkada 1 unnai cheppu manaku.
M1, M2,
M1,
M2,
M2,
M4,
and this is M4,
M7.
M7. Okay, so this is the sigma symbol. You can use the symbol. So sigma of, this is sum here. So carry is equal to sigma of, so what are the combinations here? This one, this one, this one, and this one. Okay, so carry is equal to, so sigma of
M3, M5,
M5,
M6, M7.
M7. Okay, so far this is fine. So first of all, write the truth table and identify the minterms here for sum and carry. So I told you that 328 decoder is a minterm generator. So it will, with the help of 3 inputs, it will generate 8 minterm outputs. Okay, so for this we need a block diagram here. So what I can do here is, so write the block diagram. So with the 3 inputs, what are the 3 inputs? X y, X y z. Okay, so this is a 328 decoder. Okay, so what are the outputs it is generating? So decoder A output generate చేస్తుంది మనకు. So it will generate 8 outputs, that is M0, M1, M2 till M7. So these are the outputs generated by the decoder. So draw the block diagram for this. So M6, M5, M4, and M3. Okay, so M0, M1, M2, M3, M4, M5, M6, M7. So this is a 3 to 8 decoder block diagram. Okay, so block diagram of 3 to 8 decoder. Clear? So now what I had to do, I had to implement this full adder using decoder and logic gates. Okay, so what is sum here? The sum game వచ్చింది మనకు. So S is equal to sigma. What is the meaning of sigma? Summation of minterm M1, M2, M4 and M7. So we have to add all these minterms M1, M2, M4 and M7. So adding is done with the help of OR gate. Yes or no?
Yes, sir.
Yes, sir.
Yeah, sir.
So this is M1. So where is M1? So I have M1. I have M2. Okay, this is M0, this is M1, right? So you don't confuse. ఇక్కడ కొంచెం diagram అంత neat గా వేసిండాను, but try to understand this. So this is M0, M1, M2. Wait. Okay, so M0, M1, M2. So where this is M1, M2. What are the remaining things? And we have M4, M7. This is M4 and M7. So all these four are given to one OR gate. So what is this? This is sum. Okay, this is equal to sum here. Okay, and carry. So what is carry? So carry is M3, M5, M6, M7. Okay, so we need M6, we need M7, and we need M3, M5. So we have M3 and we have M5. So these four are given to another OR gate. So that is carry. Yes or no? So clear or not? So shall I draw the diagram once again?
Clear, sir.
Clear, sir.
Yeah. So this is how we implement with the help of the decoders. Okay. So decoders are so you'll be given a problem like this. Implement using decoder and logic gates. Implement full adder or design a full adder using decoder and logic gate. So this is the decoder, and the output of full adder is this one. Okay, and we'll design like this. Okay, so wait, I'll show you with the test. Okay, so this is min terms here. So 1, 2, 4, 7 and 3, 5, 6, 7, and this is how we'll draw. Okay, so instead of I can write M0, M1, M2 and write, like itla na write, no problem. Okay, this is sum and this is carry. So 3, 5, 6, 7, this is carry, and 1, 2, 4, 7, this is sum here. Clear?
Yes, sir.
Yes, sir.
So now there'll be another set of problem, which is also a simple one. So the problems will be like this. So implement the following logic. Take on this problem. So following logic, following functions on following function on decoder logic. Okay. Okay, so the functions will be like this. So for implementing any function for decoder logic, we need minterms. Okay, so minterms, so untene we can implement. So the functions are my1 is equal to sigma of, so I'll write the sigma of 0, 1, 3, 6, 7. Symbol is sigma. Okay, and so y2 is equal to, so I'll write pi of this one. So pi of 0, 2, 4, 7. So a little bit of different problems, like koncham logic change chesintaru, and y3 is equal to pi of 1367. So what is the meaning of pi here? So it is product of sums. So sigma is sum of the products. So pi is product of the sums. So I mean these are the max terms here. Okay, so max terms are given. We have to find the min terms. Okay, so how to find the min terms? So when we know the max terms, so tell me how to find the min terms when we know the max terms. So find out this term.
K-map use
The
చేస్తాం.
remaining ones, sir.
Yeah. So no need of using K-maps, the remaining ones. So when we know the max terms, so the other terms are min terms. So 0 to 4, 7 only. So what are the remaining terms? So up to maximum is 7 here. So it is 1, 3, 5, 6. Okay. So getting my point. So whenever we have the min terms, so you can check the previous recordings. Okay. So when we have the min terms here, the remaining terms are max terms. Okay, when we have max terms, the remaining terms are min terms here. So y1 is fine. So y2 is equal to sigma of, the remaining terms are max terms here. So it is like 1, 3,
5, 6.
5, 6. Sorry, 5, 6. Okay, so y3 is equal to sigma of remaining terms. So 0, 2,
2, 4, 5.
4, 5. Okay, now I have to implement all these three functions on a decoder here. So decoder is a min term generator. So draw the diagram. Okay, so three inputs. So three inputs, because it is a 3 to 8 decoder. So I can take it as ABC and Unam. The min terms are like M0, M1, M2, M3, M4, M5, M6, M7. Okay, so when we know the sigma, all three OR gates should be used here. Okay, so 3 OR gates should be used. So 3 OR gates will add all these things here. So y1 is nothing but addition of 0, 1, 3, 6, 7. So 0, 0, 1, 3, 6, 7. So we need to draw chain. So this is given to OR gate. So this is y1. Okay, and y2 1, 3, 5, 6. So 1, where is 1? So here we have 1, we have 3, we have 5, and we have 6. Okay, so all these 4 given to another OR gate. Okay, the similar way 0 to 0 to 4 5. Okay, so last, so we can use this 0 2 4 and 5. So this is given to third OR gate. Clear?
Yes, sir.
Yes, sir.
Okay, this is how we have to implement the decoder using logic. I mean, decoder over the R kind of problem also, over D kind of problem also. Okay, so we'll stop it for today. So next class we'll see the multiplexers, concept of multiplexers. Clear?
Yes, sir.
Yes, sir.
Yeah. And drop your attendance second, Neil.